Okay, this is part 4 of the magnetic field of a long straight wire. As you can see, I have um, data collected for all of my distances, 1 centimeter, 3 centimeters, 5 centimeters, up to 11 centimeters. And I'm going to take these mu values and place them in a table. I've done that already. So let me go ahead and bring up Logger Pro so we can actually do some data analysis with the information that we have. So here's my Logger Pro. And what I'm going to do now is I want to create a graph for this data set. So I'm going to go ahead and click on Insert Graph, and I'm going to look at the graph properties, and I want to use a different run. I already have one run saved here, so I'm going to select the data that I want. I want the magnetic field magnitude and the distance in meters as my two pieces of data. So I'm going to go ahead and now click. The column should be distance in meters, and all I want from there is the magnitude of the field. So I'll click OK. Here's my graph. So let's make that a little bit bigger so we can all see it. So I'll click A. So there is my graph, and it looks really nice. It looks like there's a fall off. I want to model this data. There's a couple of different philosophies here. I'm actually going to model this data to take a look and see what the dependence of the field is with distance, the dependence of the magnitude of the field with distance. So I'm going to click Curve Fit in Logger Pro, and this gives you various options. And what I'll select is A over Z, because I'm suspecting from Ampere's law that this is a 1 over Z dependence. So I'll click Try Fit, and you can see that there's a correlation of 98.8374, blah, blah, blah. I'll click OK on that, and this gives me the model equation, the mathematical representation of my data. So I can now use this and compare it with Logger Pro, not Logger Pro, with Ampere's law, which is for a long straight wire, the magnetic field is mu naught times the current divided by 2 pi times the distance. And you see there's a very good fit, and now with the value of A that we have, we can actually figure out how much current we've actually been putting into the wire. Now, in my setup, I have actually been monitoring the current using a current meter. You don't have to do that, but you can. And if you do, my current has been on the average about 1.93. So I can go ahead and calculate that. So document. Okay, so you could actually do the analysis with this data and figure out what the current is based on Ampere's law. Well, another way of doing that would be to do another graph. So I'll do a second graph here, and so I'll insert a graph, and what I'm going to plot is the magnetic field versus 1 over the distance. Let me just fix that real quick. Not that one, but this one. And I don't want all of it. I just want the magnitude of the field. And this should be 1 over the distance. And here you have it. And look at what happens when we do this plot. So here is my plot. I'll make it a little bit bigger. It looks like a straight line. I'm plotting the magnetic field versus 1 over the distance, and it should be a straight line, and it is, with a correlation of 99%, as you can see from here. So now I can go ahead and use the slope of that line in microteslas, so be careful of your units. In microteslas, I can use the slope of this line to actually figure out what the current is in my setup. So that's it. You would probably, if you're going to turn this in, I would want the data table, and I would also want the graphs of the magnetic field versus the magnitude of the magnetic field versus the distance, and the magnitude of the magnetic field versus 1 over the distance. And this should actually give you a very good um, close approximation to Ampere's law.